I try to draw pictures. I'm not going to do them again, of a hill, a valley, and a thing called a saddle point, right? So this is the main technique we're going to use to find the local max and minimum of a function z equals f of x, y. So we're only going to do it for three-dimensional functions, right? X, y, and z, right? So z equals x cubed plus 4y squared, right? That kind of function. And we're going to use this thing called the second derivative test. You evaluate a guy called capital D. Sometimes he's called capital D brackets AB, but I'll call him capital D. And it's the second derivative at a point in terms of x times the second derivative at that same point with y. Take away the second derivative of x, y at that point squared. And the points that you choose, and I just realized I didn't put them in here, is you find the critical numbers. So you only do this test on places where you have critical numbers. So, oh, and I should have told you who critical numbers are. That's the places where those two guys are zero at the same time. So you find this thing, the second derivative value D, right? That's big D. If D is positive and the second derivative with respect to x is also positive, you're looking at a local min. If D is positive and the second derivative xx at that critical point is a negative number, you have a local maximum. And if D is less than 0, you have a saddle point. So do you see that we now have a way of telling local min, local max, or is a saddle point? So the main technique for doing this is step one, you find the two partial derivatives, those guys, and you solve when is those two things equal to 0 at the same time. And the solutions that you get to that, hopefully there's at least one solution, are called critical numbers. Or I guess I should call them critical points because they are a coordinate. Right. Once you've identified, maybe you'll find 2, maybe you'll find 1, maybe you'll find 5, right? Who knows? But you find all the critical numbers by finding the first derivative with respect to x, the first partial derivative with respect to y, find out when that guy is equal to 0, find out when that guy is equal to 0, actually when both of them are 0, and you'll come up with some critical numbers. The second thing you then do is you find that guy, and that guy at the critical numbers, right? I'm just calling them at the point AB. You get that guy. Third thing you do is you find big D, right? Big D. And then 4, the last thing you do is you test big D. And the test is this piece here, right? So that's kind of our shopping list for today. I'm going to move on and pick a question and kind of hopefully get one that goes through. Yeah, this one looks good. I'll put it on there. Have a look at it. Come on. Stop scrolling. That's too easy. Yeah, that's not nice. I'll try, that's a good one, right? I'll try to find one that has like all the features at once. So this is my version of question 5. The function that we're going to deal with is 2x cubed, take away 6x, plus 6xy squared. And this thing has a local min, it has a local max, and it has 2 saddle points. So it's got pretty much everything you could possibly want, right? Because a lot of these polynomials look like English hillsides, right? They have hills and valleys, right? So that's why you get max and mins. So first thing I'm going to do in my little hit list is I'm going to find the partial derivative with respect to x. So that's what? 6x squared take away 6 plus 6y squared. Okay. And then I'm going to do this fella, which is nothing. Okay, nothing. That's nice. And 12xy. Okay. So there's my two guys. Then we have the algebra, and I think very often finding the critical numbers, solving when are these both zeros is very often one of the hardest parts of this process, right? Because you're really trying to just getting some answers here for me, so I know if I've done it right because I've lost it. Here we go. Well, that's equation A. I'll call that equation B. Right. If I take this guy and I set it equal to 0, would you agree that there are some possibilities here? Can anybody tell me any value of x and or value of y that would make 12xy 0? And don't overthink it.
0.
0. So one possible solution could be x equals 0. Another one could be y equals 0, right? I guess both equal 0 is also true. Now, if x is equal to 0 and I plug it into A, right? Then what do I get? I get 6 lots of nothing, which is nothing. Take away 6 plus 6y squared. And doesn't that also have to equal 0? Great. And if you solve for this, and can I cut to the chase just for speed? Would you agree plus or minus 1? Which means that we have some critical numbers. X is 0, y is 1. X is 0, y is -1. Would you agree that that combination makes this 0 and that 0? You all agree on that? Right. Now, there was a second possibility. Couldn't y be 0? And I'm going to put that into A as well. And so that gets me 2x cubed, take away 6x plus nothing, and that has to be 0. Okay. Tell me some algebra. Give me something to do here. I need to solve this. What could I do to this day? I don't want to say the word because then that's me giving you too much help.
Maybe you could factor out an x.
Or even a 2x. Are you comfortable with that? Now, if you factor that out, don't you get x equals 0? Right? And if you solve for that, can I just cut to the chase and say plus or minus √3? Are you comfortable about x squared minus 3 will be 0 at those two fills, right?
Professor Robertson, I'm confused. Because you
Yes.
said put the y equals 0 into A, but you used the original equation.
Oh, shooting space. Thank you, Mia. It's not, you should be confused because I did it wrong. I scanned up here instead of scanning here. So forget that, guys. Put it into A. I'm not doing my sad story about I've only got one eye and I scan badly. So here we go. It's going to be 6x squared, take away 6 plus nothing equals 0. Actually, in a lot of ways, doesn't that look much nicer? Agreed? So that gives me two more answers, 1, 0 and -1, 0. And what we have found here are called the critical numbers. But let me tell you right now, every time you do this process, the two equations that you come up with are all, there's so many variations on a theme. Don't expect always to get, oh, you make x 0 and solve it. You got to just take what's in front of you and work with it, right? But there are some tricks that are going to be pretty common. There's very often a lot of factoring and solving, quadratics going on, or solving linear equations, or, systems of equations. I've seen questions where it's 3x plus 2y is 0 and 4x minus 5y equals 0, right? You have to say it, you have to solve a system of equations. Whatever you end up with, you solve it to get the critical numbers. And that's basically step 1 done, right? We got the critical numbers. Now, moving on, and I'm going to find f of xx, which basically means just take this guy and differentiate with respect to x, which isn't too bad. I need to find f of xy, which means take this guy, but do it in terms of y. I believe you get that. And then I want to do f of yy, which means you take this guy and differentiate him with respect to y. Right, now, based on my ability to screw things up, 12x looks good. $12y looks good. 12x. I'm pretty sure they're right. You comfortable with them? Right. Now, D has got a really, I don't know, messy formula. It's f of xx times f of yy, take away f of xy squared. I don't like putting the ABs in. I know that they have it in the textbook, but I don't like them because I want to just do this as a function of x because I think it's going to be easier later on. So what have I got? I've got 12x here. I've got 12y here, and I've got take away that guy squared. So I've got 144xy, take away 144x squared. Are we comfortable that that's right?
Shouldn't it be 144x squared?
Didn't I write that down?
No, I meant the first one.
Oh, here?
You see, you have 12x times 12y. I thought we were doing, I thought it was 12x times 12x.
Okay, we are doing f of xx, which is 12x, times f of yy, which is 12x. Thank you. And f of xy is 12y. Right. So you are right. It's 144x squared. Take away 144y squared. That's kind of pretty answer. Okay. I think I'm going to have to write things down in separate pieces of paper today because scanning's getting shot. I keep looking at the wrong things. Well, what do we now do? Well, we found D, right? Let's do our test. Each one of those critical numbers gets tested on its own. So essentially, here is x and here is y. So I'm going to find two things. I am going to find the value of D, and I'm going to find the value of the second derivative with respect to x, right? Two x's, right? At this point here. So let's see. What's D going to be? Well, D is going to be 144 times nothing squared. Take away 144 times 1 squared. And I believe that answer is negative 144. I don't need to actually calculate this bit now. Isn't that D negative? Right? At that critical number, the value of D is negative 144. If the D is negative, doesn't that mean that at that place, we have a saddle point? Are you comfortable with that? Right, move on to this one. D is going to be 144 times nothing squared. Take away 144 times negative 1 squared. That is also a negative number, and that is also a saddle point. Okay. Right.
Shouldn't that be a positive number?
Well, negative 1 squared is 1,
Oh,
and negative times that. But it's worth checking with me because I'd rather people check and then I'm right than let something slide, right? And, you know, nothing works out the way it should because of that. Right. So it looks like we've got 2 saddle points. That's great because that's what the answer says there is. Let's see what happens at this one here. It looks like D is going to be 144 times 1 squared. Take away 144 times nothing squared, which is positive 144. Okay, now when it is positive, don't we also need to check what the second derivative is like, right? Which is this guy here. So I'm now going to do the second derivative at 1, 0. And the second derivative is 12 times x, which is 12. So what do you get when D is positive and its second derivative is also positive? Well, when that happens, you get a local min. Are we good? D is positive number. The second derivative is a positive number. When those two happen, you have a local min. Right, the last one, which is this one here, it's 144 times negative 1 squared. Take away 144 times nothing squared. Also ends up being 144. And the second derivative at that point is 12 times negative 1, which is negative 12. And when you get a positive D, but a negative second derivative, that combination gets you a local maximum. How are things looking? Are we comfortable with what I just did here? Right. Now I'll show you an idiosyncrasy of WebAssign. It asks us to write down saddle points. And in saddle points, in that box, you put the coordinates of the 2 places, right? That point, comma, and that point, which is exactly what I would have expected, right? Tell me the coordinates, right, of where the saddle points are, right? And that's these 2. It then goes on and it says local max values. And then it says local minimum values. Now, if I was doing WebAssign, you know, I would probably get you just to tell me the coordinates of the local max and min. Right. So in other words, you would just say the coordinates of the local max was at negative 1, 0. Right. So it would be negative 1, 0. And the coordinates of the local minimum would be at 1, 0, right? That's what I would have done. But they don't want you to do that. They want you to tell me what the local maximum value is, which basically means find the value of the original function. Here it is, that guy there, at this point. So the answer that you will put in is not the coordinate of the local max or min, but the value of the function at the local max. So let's see, minus 1, 0. So that's negative 2, add 6 is 4. 2 take away 6 is negative 4. So that would be the numbers that you would put in. Do you see you'd put in the value of this function here at negative 1, 0 is 4, and the value of this function at 1, 0 is negative 4. And we are finished. They're quite long questions. You agree there's a lot to do in one of these. And I would assume that when you're doing homework, you certainly could cut a few corners. Couldn't you do a lot of those calculations I did in your head? Right? You wouldn't need to physically write everything down. So, you know, figure out what it is. But for the midterm, will you write everything you can possibly think of? Because if you make a mistake, as I did, for instance, at least you'd be able to show me that you were in the right place, right? You knew what to do, even if you kind of got it mixed up. Right, I'm now going to try something that won't work, but I'm an optimist, so I'm going to try it anyway. And I'm going to see if we can actually draw that function and find those 2 local min and max and find those 2 saddle points, right? Just to see them, right? So clicking on this guy, clicking on that guy. Here we go. Class resources. And I'll try GeoBra since it's the first one that's here. Okay, are you looking at GeoBra? We are good to go. Right, so I'm just going to type this guy and hopefully I can just call it Z equals. It was 2x cubed. Take away 6x plus 6xy squared. Everything is in darn capitals and nobody shouted at me and said, why are you doing capitals? And I may have to change this to f of xy. That happens fine. Okay, there we go. This here is the shape that we've just been dealing with. Right, now, can you see a local maximum where my mouse is? If I orientate it, there, can you see a kind of hill? There, you see it now? I bet you that is the guy that we found at -1, 0. Right, now there should be a local minimum. I know they've kind of cut the top of it off, but can you imagine that went a little bit lower? Do you see it there? Now there should be 2 saddle points. There's one. It's trying to get the orientation quite right. Right, do you see there? There's the saddle point. It looks like it's a max, but if you orientate it, okay. Are you just going to trust me? I can see 2 saddle points. I just can't. I'm not here. I can zoom in. Why didn't I think of that already? There we go. Can you see that funny, weird crossing over thing that's going on here? There. Do you see it there? That's a good angle. I got lucky. You see that? That's a saddle point. That's what they look like. Right. They kind of look like a saddle. And that is half the day gone by and we've done one blinking question. So I'm going to do the most efficient thing I can think of doing here is not the whole process because it takes too long, but the parts of the process that cause the most trouble. And that is finding critical numbers. Because once you've got the function and you've got the critical numbers, can't you get the D and do the test, right? I mean, it's just number crunching from that point onwards. So let's focus on just finding the critical numbers. So question 2, I'm going to get back to my white screen. Just to show you the different types of algebra that you end up having to work with. Right, so polynomials are very common with these questions because the algebra is horrible if you don't do it that way, right? Tell you what, let's just call it f of xy. Right. Partial derivative with x, 2x plus a y, nothing else. That should be 0. Partial derivative with respect to y, 0, x, 2y, oops, plus a 7 equals 0. So there's my 2 equations, A and B. Double check. With respect to y, x, 2y, 7, good. With respect to x, 2x, y, nothing. We're good. Okay. This particular combination, I would probably rewrite just a little bit differently, at least to start with. Don't need to tell me the answer, but what method would you use to solve that particular situation?
System of equations.
It's a system of equations. Couldn't you do either by the addition method, sometimes called the elimination method, or by the substitution method? I'm going to do the substitution method because I want to. 2x plus y equals 0. That makes y equal -2x. I'm now going to put y equal negative 2x into the second equation. And so x plus 2y equals negative 7 becomes x, add 2 lots of negative 2x equals negative 7. Eventually that gets me negative 3x equals negative 7, which gets me x equals 7/3. I didn't say it was pretty, but unless I've screwed up somewhere, well, I can tell you right now, it is the correct answer. It does say 7/3. Right, once you know x, don't you find y by just going back here and making negative 2 times x, and the value you get is that one. So in this question, there's only one critical, right? One critical point. 7/3 and negative 14/3. From that point onwards, can't you find the second derivatives, find capital D, and then do the test? And I don't know if that's a local max, a local min. It might even be a saddle point, but that would be your job. If it doesn't have any, you put DNE in capitals, because there's only 1 point, so it can only be one of those 3 things, and the other 2 things will be DNE. Let's see what's going on here. Now, it's a system of equations. I don't need to do that anymore. That's a system of equations. Good. Don't need to do that. Okay, this is question 4. Okay, I need to find 2 partial derivatives, one with respect to x and one with respect to y. Do you think the way this equation is written is helpful for finding those things? Do you think that's, could I just leave it and go for glory, right? I would suggest that it's a good idea to FOIL this out. Right? Otherwise, you'll get caught up with product rules and you might not quite remember which bit is the variable and which bit is not the variable. And then you still have to multiply it all out and then collect time like terms. So by the time you're finished, it's the same amount of work. So I might as well just bite the bullet and do a FOIL. So it's a 9x, a negative x squared y, a negative 9y, and a plus xy squared. And I think that's just much easier to deal with, isn't it, as far as differentiation goes? So here's our 2 guys. 9, take away x squared, nothing, plus a y squared. And that's going to have to equal 0. And if you do it with respect to y, you get nothing. You get a negative x squared. You get a negative 9. And you get what we have here is 2xy, I believe, equals 0. Let me check on this.
Would the f of x, wouldn't the middle term be 2x?
This one here?
Yeah, or 2xy, sorry.
Yeah, that's good. Yeah, that looks much better. So here is the 2 equations that we've got. Kind of interesting looking. I'm just going to see what I can do with them. I'm going to do a y squared, a negative 2xy, and a plus 9. And then the other one, I'm going to put a plus 2xy there, a minus 9 there, and a minus x squared there. And I now have an idea. This is not the only way to do this. I'm sure there's 2 other ways. But the way I've written them right now, has anyone any idea what I'm going to do next?
Add them together.
I'm going to add them together. In which case I'm going to get y squared, take away x squared, they kill, and that's 0. Well, you might think, well, what good is that? That's actually quite good. Because don't we now get a factoring? Now that's going to give me two situations. Situation one is y could be equal to x. So let's deal with y is equal to x. If you make y equal to x, can't you go back to this fella here, for instance, and replace it? So instead of 9, take away 2xy plus y squared is 0. You can now have 9, take away 2x times another x, plus an x squared equals 0. And that becomes a 9, take away x squared is 0. And that gets me plus 3 and minus 3. And since y is equal to x, that gets you a y of 3 and a y of -3. Do you see I now have 2 points? 3, -3. One of these, yeah. So the 2 points that I've got, I wish I'd read, I'll put them in red down here. I've got a 3, 3, and I've got a -3, -3, right? That's that one done. Now, the second possibility,
Paper up.
sure. The second possibility is going to be that y from here could be -x. And I'm going to use this one again. And that becomes -2x times -x plus -x squared equals 0. And that's going to get me 9 plus 2x squared plus x squared equals 0. And that's going to get me 9 plus 3x squared equals 0. And that's going to get me no solution. So there's nothing going to come out of that choice. And so there's my two critical numbers, right? 3, 3 and -3, -3. Now I'm saying that's not the only way that you could actually solve this question, right? Has anybody got another idea of how you could solve this system of equations? I decided just to add them because it seemed a reasonable approach. Anyone got another suggestion that might work? Couldn't I rearrange them then to find out what 2xy was equal to in equation A and what 2xy was equal to equation B, and then match them together and solve it that way? That would have worked. Right. Basically, you try to reduce the number of variables going on to a manageable amount. And you begin to see why getting the critical numbers is going to be the hard part of this question. Because once you know that, the rest is process, right? Second derivatives, D, plug in numbers. If it's positive or negative, boom, your answer. That's where the fun's going to be, trying to make that happen. So let's see what the next one looks like.
I have a quick question.
Yes.
Why were there no solutions for the second one?
9 plus 3x squared can never be 0. I mean, if I took it a couple of lines further, we could probably show you. 3x squared would have to be -9. X squared would have a -3, and we're only looking for real solutions, so it can't exist. That was the reason why.
Okay, that makes sense. Thank you.
It's what are we off to next? I'll just keep going through these until I run out of room or time. Did I do question 6? I've got a deja vu feeling, but they all start looking the same. Did I do 6 as the first one today, or was it 5?
You did 5 for the first
Okay,
one.
so, right. So this one just kind of looks like 5, so that's probably where my brain was. So I have this fella. Whoa, okay. Partial derivative with respect to x. 3x squared, nothing. Take away 6x, nothing. Take away 9 equals 0. Okay, that is different. That's nothing. 3y squared. Take away 12y equals 0. Okay, there's our two equations, right? We're looking for critical numbers. Values of x and y where both are 0 at the same time. Any ideas where I'm going next? When you look at these two equations, is there anything that you could do to solve them?
Move a 3y. Or
Oh, well, let's take this guy just as he is, right? Okay, so I'm just focusing on B because I want to, right? Where would we go next? I want to solve this equation. What would be a good piece of algebra to do next?
A lot of 3y.
Agreed. Would you agree then that this generates two situations? One called y equals 0 and the other called y equal 4. Are you happy about that? Okay. Now, I've used equation B to do this. Don't you then use those values of y into the first one, right? Typically. But guess what? There is no y's in the first one. That's fine. What does that mean I have to do? Well, it means I have to now solve, and I wish I hadn't drawn that line anywhere near as big. Don't I now have to find out when that is true? Right. So these are good answers. What we don't know yet is what the x's that go with them are. I have 3x squared minus 6x minus 9 equals 0. Give me a place to go. Algebraically, what would be a good idea to solve this one? Always be on the lookout to make your life easy.
I'd start by taking a 3 or taking 3 out of the equation.
Would you agree that that quadratic is a lot easier to solve than the one we had a minute ago? That's why we did it. Okay, give me the two factors for that quadratic.
Is it minus 3 plus 1?
Minus 3 plus 1. Which means that we have a solution that x can be 3, which is good, and which means x could be negative 1. Now we have to figure out how to take these two guys and these two guys and put them together. What this says is that as long as y is one of these numbers and as long as x is one of these numbers, you will get a solution, which means then that you can have, let's start again, which means you can have an x of 3 and a y of 0, an x of 3 and a y of 4, an x of negative 1 and a y of 0, and an x of negative 1 and a y of 4. Are you comfortable about how I found those 4 critical numbers by combining these two together? Right. Now, have you noticed that I think every single question we've done today has been different from every other question? Have you seen the algebra differences? Right? You know, sometimes you add the equations together. Sometimes you get a system of equations. Sometimes you get two separate quadratics and then you have to combine them. It's almost like every question is trying to be different from the one that came before. Okay, I definitely have time to do one. I'm not sure if I have time to do two, but I'll try. This is a version of question 7 then. And they have a little restriction up here. That's almost certainly because you don't want an infinite number of answers. If you do a partial derivative with respect to x, you get nothing and you get negative a cosine, so 2 negatives make it a plus. You get 6y sine x. Okay, and that's going to have to equal 0. And if you do a partial derivative with respect to y, you get 2y take away 6 cosine x's equals 0. Okay, I'll call that equation A. I'm going to call that equation B. I do not want to go anywhere near solving that guy, although I could if I tried, but I think it would be messy. I certainly wouldn't get a number, but I could rearrange that and tell you that y is 3 cosine x, which you could do, right? I'm going to use this one. 6y sine x has to equal 0, right? And that generates 2 situations. One of them is y equals 0, and the other one is that sine x, oops, don't know why there's so many ends, that sine x equals 0, right? Which in turn, doesn't that make x 0, x equals pi, and technically x equals 2 pi and 2 million pi, but because you put that restriction on it, isn't that the only 2 that you can use? So it looks like we have 3 situations. I'm just going to rewrite them again. Situation 1 is y is 0. Situation 2 is x is 0. And situation 3 is x equals pi. And for each one of those situations, and we got them from A, we now use them in B. So if y is 0, right? If y is 0, what do we get here? We get 2 lots of nothing, which is nothing. Take away 6 times cosine of x equals 0. That means that 6 cosine of x is 0, which means cosine of x is equal to 0. And x is what? Cosine is going to happen at what? At pi upon 2. And the other place is going to happen at 3/2 pi, which is too big. So only going to use that answer. So I have got my first critical number. And I've just put it the wrong way around. I've just got my first critical number. Are you happy where that one came from? Okay, now I'm going to do x equals 0. Again, I'm going to plug it into here. And when you do x equals 0, which is the guy I'm using, into here, right? I don't know where that came from. God, I have to cover things up with my scanning. 6y sine x. 6y sine x. And 6y sine x gives me 6y sine of 0. That's equals 0. Which means nothing. Oh, that dies. I've got an arrow on it and nobody told me. I covered the wrong one up. Even when I do it right, I do it wrong. So it's 2 times y, take away 6 cosine x equals 0. So it's 2 times y, take away 6 times the cosine of 0 equals 0. 2 times y, take away 6 is 0. 2y equals 6. There we go. Y equals 3. I now have a second solution, 0, 3. I get an idea. Why don't I do that so I don't scan it wrong? Now, x equals pi now. 2y, take away 6 cosines of pi, has to equal 0. What is the cosine of pi? What number is it?
-1.
-1. So 2 negatives make a plus. So you're happy about where the plus 6 came from? Which makes 2y equal -6, which makes y equals -3, which gives me pi, comma, -3. Whew, that's a lot of work. Can you see that I've now found the 3 critical numbers? And I think putting a pen on over might help me for the next question.